Hey Tim, let's have a look at how to differentiate products. We've done a lot of differentiation using the chain rule. We've learned how to differentiate polynomials, e to the x's, cos and sine, and even ln x. So what about this product rule? Well, if you have two functions that are multiplying each other, there's a certain trick to how to differentiate it. We've used the sum rule. The sum rule with polynomials, if you have two distinct functions and add it together, you just have to differentiate them independently. So if you have u plus v, then y dash equals du dx plus dv dx. And we write that as u dash plus v dash, just because we're a little bit on the lazy side. So for example, if y equals 2x to the 3 plus 5x, then y dash would be, bring the 3 down in front and multiply it by the 2, gives you the 6x squared, and then the x to the 1 becomes x to the 0, so it's just 5. Now, if we look at the product rule, how does that work? If I have y equals u times v, then y dash equals u dash v plus uv dash. Now, unfortunately, I'm not going to be going into the proof of that, but it's just something, it's a tool that you need to use when you spot two functions that are multiplying each other. It's very important to be able to recognize it, when to go dive in and use the product rule, or when one can use the chain rule. So let's do some examples here. Let's differentiate a few expressions. Here we have y equals x times sine x. So u is x and v is sine x. So y dash equals u dash, which is just x differentiating the x, times sine x, plus, now you leave u as it is and you differentiate sine x to become cos x. And there you have it. Here's another one. Y equals x e to the 3x. You can see my first function is x, and my second function is e to the 3x. So y dash equals 1, differentiate the x, and you leave the e to the 3x as it is, that's v, plus x. Now you leave the u as it is, and you differentiate the v. You can see here I've applied the chain rule, so it's e to the u. Differentiating e to the u remains e to the u, and then you differentiate the u, which is where the 3 comes from. Then here's a little bit of more of a complex example. Y equals sine to the 5x times cos to the 3x. Now this is very important. I've written this out as sine x to the 5 cos x to the 3. I strongly advise that you do this. It just makes it easier to see the different functions, and there's less likelihood of errors. So make a point of always writing something like this. Put the index outside of a bracket. It'll reduce a whole lot easier. So y dash equals, well, let's see. We recognize that there's a u inside. So the u function, the first function we're multiplying is this one here. But within my u, I've got another u. I've got a sine x. So it's almost like u to the 5. So we differentiate him. We bring the 5 down, and it becomes sine to the 4 of x. But now we must also differentiate the u, which is sine x becomes cos x. And then we must leave this guy alone as he is. Okay, so we leave him as he is. That's the v. It doesn't change. So I've had to differentiate u and times him by v unchanged. Then we leave u just as he is. So we leave the sine 5x. Okay, and now we're going to differentiate v. So we look here, there's our v. You can see v's got another function inside of him. So we bring the 3 down. It becomes a cos squared x. And then we differentiate what's inside the bracket there. Our next layer of u, which becomes minus sine x. And now you can just rearrange the terms. And you can say, well, that's cos 4x. That's sine 4x. And there's a 5 in front. So always bring your numbers to the front. And then leave your multiply out whatever sines and coses you have in the term. And here's a similar example. Y equals sine to the 4 2x cos to the 3 5x. Again, I've written out those expressions with the index on the outside just to make it easier and less likelihood of mistakes. And you can see that y dash equals, well, let's bring the 4 down. Okay, the sine 2x to the 4 becomes sine 3 to the of 2x. And then we need to differentiate what's inside the u here, which becomes a cos 2x times 2. See there, cos 2x times 2. And then v remains as it is, which is that term over there. So he remains as he is. Then we leave the u alone, we leave him just as he is there, and then we differentiate the v. And you can see there how 3 comes down, becomes cos 5x squared, and then we need to differentiate what's inside the bracket here. It's like the mini u inside the function. It becomes, bring the 5 to the front, and cos goes to minus sine. So it's minus sine 5x. So these are quite easy, and you always combine the product rule with the chain rule. So you're differentiating one of the functions, and when you're differentiating that function, either u or v, you then use the chain rule to break it down further. Here's an example with the e to the x. So we have y equals e to the ax cos bx plus pi by 2. So y dash equals, well, differentiating e to the ax gives you a e to the ax, and then the cos bx plus pi by 2 remains just as it is, and then you leave the u alone, and now you need to differentiate your cos bx plus pi by 2 term. So differentiate the inner part, you bring the b to the front there, cos goes to minus sine, and the inside the sine just remains unchanged. I think one of the important things with the chain rule is that you stick very carefully to the format. In other words, if y dash equals u dash v plus uv dash, don't get in a rush and say v times u dash, or do the u dash v and then think I'll do v dash times u, because especially when you're checking your work, it's very, very useful to keep the structure like this. So you differentiate u, you times it by v, and you leave u as he is, and then you differentiate the v. So there you go. Here's another example. Find the points on y equals x sine x at which the tangent passes through the origin. Since we're talking about the tangent, we know we're going to be differentiating. We're going to need to find the slope, and because we can see an x sine x, we know that it's going to be using the product rule. Now, what does this graph look like? It's quite interesting, because as sine x changes, sine x, as x increases, sine changes from minus 1, or from 0 to 1 to minus 1. So it's bounded by minus 1 to 1. Whereas x is just steadily increasing. If we start from the origin here, we can see they've plotted the line y equals x, which is at 45 degrees, and you can see how the sine value starts off as a normal sine wave, but it's bounded by y equals x. The maximum of the sine graph is going to be x. Okay, and then you can see how it's mirrored around the y-axis. You can see that because x is negative in this area, so you're actually plotting minus sine of x. So therefore, it's actually 180 degrees out of phase with the positive half of the x-axis. Just out of curiosity, it's quite an interesting waveform this, but out of curiosity, what do you think the wave would look like if it was y equals x squared sine x? Well, it's very similar. Okay, you're going to have a y equals x squared graph here, and you're going to have the sine wave would be bounded by that. So it's quite interesting. But in this case, okay, we put the y equals x squared. In this case, there isn't, because x squared sine x, because on this side the x squared is always positive, so now it's not mirrored around the y-axis. So in other words, the sine wave still follows its normal pattern of going negative there. Okay, so you see that it's not mirrored around the y-axis. Well, what about y equals x to the 3 sine x? Again, your normal x to the 3 graph is going to look something like that. Okay, and now we can use him as the bound of the sine x, and then we're going to have a similar pattern where it's going to emerge like that. And this one will look similar to the y equals x graph, where it's actually mirrored, okay, in the y-axis, because now it's an odd function again. So these are interesting curves that emerge out of these functions. Anyway, let's get back to our graph, which is y equals x sine x, and let's do a bit of differentiating. So first of all, we need to find the tangent. So we say y dash equals sine x plus x cos x. See, I've applied the product rule. We're differentiating the x. It's just 1. Sine x remains. Then we leave the x as it is, and we differentiate sine to get cos. Okay, then the second step is to find the equation of the tangent. But it says the equation of the tangent must pass through the origin. So in other words, the equation of the tangent must pass through the points 0, 0. So our normal form will be y equals mx plus c. In this case, it's just y equals mx. So now we found m, so we can say that y equals sine x plus x cos x times x. And then the last step is to find the coordinates of the point in terms of x. So we've got some point where we have a tangent going through an origin. Okay. So say the tangent is over here. You can see it's going to be somewhere there, and there it's got to go through the origin. So now we can say we know y equals x sine x. So x sine x equals sine x plus x cos x times x. So there's going to be some value x where this condition is satisfied. And if we simplify and expand the expressions, okay, we get x sine x minus x squared cos x. Just multiply out these terms here, and that reduces further to x squared cos x equals 0. So your x sine x's just cancel out. So now we know that one of the points is going to be at x equals 0, which is not very helpful. It's just a point. It's not really a tangent through a point. And then we can say, well, cos x is equal to 0. So that happens at 90 degrees, 270 degrees, etc. We can use the product rule to differentiate quotients. And it's easy to prove. For example, if we have y equals u divided by v, then y can also be written as u times v to the minus 1, which is simply two products of two functions. So y dash equals, well, u dash times v to the minus 1. That function remains as it is. And then plus u times, now we must differentiate v to the minus 1. Bring the minus 1 to the front. It becomes v to the minus 2. And then don't forget, you also need to differentiate v. So we call him v dash. That is like using the chain rule. Okay, so you've got a v to the minus 1 and you want to differentiate. You also need to differentiate the v itself. So that reduces further to u dash over v minus uv dash over v squared. And now by putting over a common denominator of v squared, we can say that our quotient rule reduces to u dash v minus uv dash over v squared. And that is what's called the quotient rule. So it's very similar to the product rule, except you'll see there's a minus there. The structure is similar. U dash v used to be a plus, now it's a minus, and then uv dash. Then you divide the whole lot by v squared. So it's pretty easy to remember. Just think of the product rule, and there's these two minor changes here that you have to introduce. Let's use the quotient rule now to differentiate tan x. Well, you know that if y equals tan x, it's equal to sine x over cos x, which is like saying u over v. So we simply differentiate u. U dash becomes cos x times by v. You see there's v. And then minus u, leave u as it is, sine x remains, and then we differentiate cos x to get minus sine x. And you put the whole lot over v squared, which is now cos squared x. This reduces to cos squared x plus sine squared x over cos squared x, but we know that cos squared x plus sine squared x is 1. So 1 over cos squared x, but that's simply sec squared x. So the differential of tan x is sec squared x. Now this is a very useful equality to remember, and also obviously the integral of sec squared x is tan x, and this you need to know. Okay, the integral of sec squared x is tan x, and don't forget your indefinite integral constant over there. Now this is unusual because it's something that we have to memorize. You won't have time to prove something like this in an exam, so just keep an eye on him. This is one of the rare cases where we integrating something that's complex. You see, it's not in the form ax plus b. It's not just a sine, an integral of a sine, or integral of a cos, or integral of e to the x, or integral of a polynomial. This is actually a complex function squared, and it just happens to reduce to this tan x. So it's a very special case, and that's why he needs to be remembered. And we can use him in an example like this. For example, find the integral of sec squared 2x minus pi over 3. Now, do you recognize the ax plus b? Okay, a is 2. So now we can say, right, we integrate sec squared, it becomes tan, and the inner function remains just as it is. The ax plus b remains as it is, and we put a 1 over a in front. And there we've done the integral. Here's what you must know from this section. First of all, there's the sum rule, which says if you have a y equals the sum of two functions, u plus v, then y dash equals u dash plus v dash. Then we have the product rule, y equals u times v, then y dash equals u dash v plus uv dash. Then we have the quotient rule, which is y equals u over v, then y dash equals u dash v minus uv dash. See the similarity of the product rule, just with a minus, and then we divide it by v squared. Then there's a special case, where if y equals tan x, then y dash equals sec squared x. And obviously from that, the integral of sec squared x is tan x. And don't forget your indefinite integral there. Just like we did with the other differentiation examples, we can use the product and the quotient rules to find stationary points and min-maxes in much the same way as previously. You can either use the double differential method, or by checking if a function, or if the y dash is increasing or decreasing on either side of the critical points. So the rules are the same, and the questions are similar. They might ask for min-max, stationary points, or equation of tangents, or even equations of normals. These are all similar. It's all similar things. It's just nice to have the product rule and the quotient rules to rely on to be able to do more complex functions. And then always combine the product and quotient rules with the chain rule if you need to. So as soon as you have a more complex function, don't forget to differentiate throughout the function, so you don't leave any steps out. So that's all from me. Thanks for listening. One last tip is that you need to do lots of examples like this to make sure that you don't make mistakes. And you need to know the chain rule well. So get on top of the chain rule, and these things become quite simple. So thanks very much. If you need any questions answered, or you want me to have a look at an example, feel free to email me. I'm more than happy to help. Ciao.